Okay, this is problem 8. I'm going to be pulling the board down for a little while. The problem here is this is nomenclature. Name the compound for the corresponding formula, or write the formula for the corresponding name. And this, whether the thing to remember the whole time when we're dealing with nomenclature, with naming something, or with writing the formulas, is the homology of the whole thing. Homology is the study of how things transform, and we use that to understand the periodic table. When you understand the homology of something, you understand how it transforms, and two things that transform in the same way are homologous. So once you know the homology of one member of a group of homologous items, you know the homology of all the members of the group. So you only have to learn the homology of one thing, and then you know the homology of all the others. And this is going to help us a great deal with understanding things like nomenclature, the periodic table, and a lot of things in chemistry. So recall that when we started out nomenclature, we started with ionic compounds, simple binary ionic compounds to begin with. And there we established the following protocol. We started with the cation first, and we gave that the element name, and then the anion came second, and it was given the stem name from the element with the "-ide" suffix. And then we go from simple binary compounds to molecular ions, and then we're going to stick to that fundamental protocol. The cation is going to come first, and then followed by the anion. And then we're going to have to take into account certain aspects of whether if it's a metal cation, whether it's a fixed charge cation. And if it is, then it's going to be easy. If not, then we're going to have to call out the charge in the name. And then we have to take into account with molecular ions, the number of oxygens, the oxy anions. And then the number of oxygens is going to have, there's two possibilities. If there's two possibilities, one with more oxygens is given an 8 suffix, and then give the name of the other non-oxygen element. And if it's got, the one with fewer is given the "-ite" suffix. When there are instances of more than 2 possibilities, where there's 4 possibilities, we're going to keep the 8 and the "-ite" protocol. We're going to extend it to give the one with the most number of oxygen is giving a "per" prefix and an 8 suffix, and the one with the fewest number of oxygens is given a "hypo" prefix and an "-ite" suffix. Then we're going to have to go from there to acids. And an acid is a material that is going to be a source, for now, a source of hydrogen ions. And because we cannot name everything after the cation, they would all be hydrogen this and hydrogen that, we will, when they're in water, we'll call them an acid. And we'll have several protocols that go with that. I won't delve into them now, we'll discuss them in class. And then we're going to have to deal with last, what we do with it when we do place them in water. Then we're going to call the 8 is going to become ic acid, and the "-ite" is going to become us acid. And there are several other things we're going to have to follow. When we get to the molecular compounds, we're going to find the most metallic of the elements, and it is going to become, it's going to be written in the formula first. And this is also going to be a protocol followed when we write the formulas for molecular ions. The most metallic element is written first. So we're back to the homology of the periodic table and how it relates to the names. And we're trying to name things in such a way that it is unambiguous. And this has taken a great deal of time to develop. The first compound we have to name is a salt. It's not a binary salt. I have molecular ions and I have a metal. So the metal cation is the strontium metal. This is a fixed charge metal. The fixed charge metals are group 1, group 2, and zinc, cadmium, and silver, and aluminum. Those are the fixed charge systems. Beyond that, there is more than one type of charge. So we're going to have some sort of strontium. The metal, the cation name goes first. So it's going to be strontium. And now I've got an oxyanion for the anion, and it's going to be named after the non-oxygen element. So it's going to have the stem name from that, and it's going to be phos first, because this is phosphorus. So it's going to have a phos prefix. And now it's going to be named depending on how many oxygens present. Well, with phosphorus and nitrogen in group 5, there are 2 possibilities. So there can be 3 or 4 oxygens with phosphorus. 4 would be phosphate, 3 would be phosphite. So in this case, it's phosphate. So it's strontium phosphate, because this is a fixed charge metal. So, named after the cation, followed by the anion. Now, the second compound, I'm given the name and I have to write the formula. Again, this is a salt, potassium chlorate. Well, potassium, self-evident. It is a group 1 metal, it's fixed charge, so I've got potassium, and I've got, you know, the chlorate ion. This is an oxyanion. In this case, with the halogens, we have 4 possibilities, and this is given the 8 suffix, so there is the possibility of 1, 2, 3, or 4 oxygens. The 4 would be perchlorate. 3 oxygens would be chlorate, so it's potassium chlorate. They all have the same charge, and that is going to be potassium is +1, and there are 3 oxygens. So potassium chlorate, that's again pretty straightforward. Now, here with this third compound, this is the cation is going to be hydrogen ions, and I've got an oxyanion here, but it's in water. So a hydrogen ion in water is an acid, so it's going to be some kind of an acid. Now we have to name it because all acids are usually named after the anion. And so this is a sulfur oxyanion, which would be, of the 2 possibilities that exist with sulfur, it could be SO3, which would be sulfite. SO4 is sulfate. 8 becomes ic when it's an acid. And so this is sulfuric acid. So and now the next one is an instance of, this is a binary salt, a metal, non-metal combination. Binary means there are only 2 elements there. Didn't necessarily say there was only 2 atoms there, but only 2 elements. And now, because iron is a transition metal, it is found in more than one possible ionization state, so it's charged. In this case, it's +3. So iron +3, and it's an oxide. Now what you want to always remember, and we'll do this on scratch paper, we have for every cation, which is N plus, and anion with M minus charges, in order for it to be electronically neutral, you do the following. It's going to have a formula that's going to be CMAN. So whatever the charge number on the anion is going to be the subscript suffix of that cation in the formula. And whatever the charge was on the cation is going to be the subscript suffix of the anion. And this guarantees that it's going to be neutral. So if I've got iron 3, I've got Fe, and it's 3 plus, and oxygen. Remember, the charges on the nonmetals is equal to the group number minus 8. It's very easy to find. You just go from the noble gases and start counting backwards, and that's the number of charge. But it's also the group number minus 8. Oxygen is group number 6. 6 minus 8 is 2 minus. So in order to get this formula, it's going to be Fe2O3. That means I've got 2 plus 3 charges, which is plus 6, and 3 2 minus charges, which is minus 6. It's electronically neutral. They always have to be electronically neutral. Nature abhors a charge, and all of my creditors abhor me charging. So this is going to be a very simple way of guaranteeing that they're always going to be neutral. And now we can write the formula for iron 3 oxide. Is going to be Fe2O3.